So friends, we have discussed very intimate concepts related to operations management. There are two more elements. One is root cause analysis, and other is failure precursor analysis. So these two aspects have to be discussed. Why? Because any incident happens in the plant. The root cause analysis, whether it should be done or not done, because root cause analysis is a very resource consuming activity. So ideally speaking, it should be done for events where the returns are very high in terms of improvement in safety. Okay, and precursor analysis is basically is there any way to get the signal of any failure in advance, number one. And number two, is there any way to assess their impact, and how they happen? So these are the things we will discuss in this lecture. Root cause analysis program, it is a traditional approach to understand failure, especially events, how they happen. These investigations are generally, even if it is a very primitive thing or any brainstorming sessions, they are called root cause analysis. And a typical results of any root cause analysis is identification of human root. Just as a symbolic thing I am presenting here. Okay, so these were some failure mechanisms, and then we want to identify, it is an effort, why it happened. So these are the roots, why it could have, in fact there can be one or more roots for the accident to have happened, and somebody has to analyze the root and what was the cause and how it can be corrected, how it can be addressed. And typically till we reach the human roots, we go on doing the analysis. Okay. Once the human roots are identified, then we say, okay, whether it will require some improvement in training program, or it will retraining, or it is some gap area in training, or there was some issues related to human factor in operations that need to be understood. So that's why this root does actually. There were four major components of root cause analysis traditionally. So first is, if any incident has happened, then immediate visit to the site and collect all the information, what we saw, what we found, what was the noise level, how it affected the area, how it affected the plant. But then the objective is to collect before we clear the plant and have a cleanup mechanism. We have to collect the information, what kind of signature material they were found. So data collection is one thing. Suppose if there was a bearing failure, very important bearing failure. So any symptom which can help us in understanding the event, because plant will come to halt, and if it is a safety rated equipment, then it becomes a safety issue. So then all the informations are collected and they are arranged in a chronological order. It's very important. Based on the symptoms that are available in control room at the site, arrange them in the chronological order, and then expert brainstorming sessions happen. And some analysis if required, that also forms part of it. And look for the roots, whether it is a design route, operation route, maintenance, environment, aging, what was the route that was available, and accordingly. And root cause failure means it is mapped on many other similar things also, so that benefits can be accrued in when one incident happened and another similar incident should not happen. One of the criteria for a success of a root cause analysis is that type of event should not happen in the plant again. Not only for that component, but for any component. So that is a quality of the root cause analysis, that defines the quality of the root cause analysis. But if we find ki, even if a frequency of that failure is reduced significantly, that itself is also an achievement. But if our feedback program or follow-up program doesn't show these two things, that is frequency is also not reduced, and it is happening in other plant on the same component and other component also. That means the root cause analysis was not a validated root cause analysis. So this is what. And then the worst part is when we incorporate any change suggested by the root cause analysis or modification, that modification should not result into any event which has got a safety significance. Okay, so one has to not only implement correction, but we have to see that it doesn't add to another failure modes or mechanisms into the system. So this is the background of root cause analysis. Insights that we are available from root cause analysis, traditional approach to root, it was realized that brainstorming tends to be subjective at times, and root cause analysis is a very, very serious exercise. We looked at the ultimate objective of root cause analysis after understanding the root causes and implementing the suitable corrective action mechanism, failure mechanism. And then after implementing those things, the event should not repeat. In fact, there have been some unique experience, but they are very isolated actually. That some new failures has been got inducted into the system, which was realized over a period of time. This time could be next moment, or it could be one year, it could be 5 years. So this situation should not arise when we implement any change as part of root cause analysis. So what was thought that the depth of the root cause analysis should increase. Root cause analysis is though a lot of insights are available from brainstorming session, because expert from maintenance, operation and related areas, specialized in those components, they are all available. But then if we have to understand why the failure had occurred, one has to go to the not all root causes, serious root causes, serious failures. One has to go to the material level, simulation of the simulation experiment, either it could be testing also, and then repeat the phenomena, how it has come, and demonstrate it, and then provide a corrective mechanism. Now that corrective mechanism also should be a validated corrective mechanism, and all those things come from interview that grassroots level people, and then having good insight on failures, and then whether it was a material selection problem, it was a maintenance related issue, or if it was a maintenance related issue, where was the weak link, how the component was replaced, something like that, and whether there was approved procedure followed, so many quality of the how any change we do, it should have a quality mark, and whether that quality mark was missing. Quality mark means it is organizational input, so that means approved procedures are being used. So all those things. And now role of PRA in root cause analysis. So in PRA, as we said, one thing is if we have a n number of events that has happened in the plant, as I mentioned initially, for all the events, root cause analysis is not required, for one very simple reason. Root cause analysis is a very resource consuming exercise, whether it is a manpower, whether it is the finance that is required, time required to do the root cause analysis. So in nutshell, very important events which have safety significance only should be subjected to actual root cause analysis, and there PRA helps in identifying the risk connotation attached with the, because we can see the failure, and then we can identify those cut sets also, and in those cut sets which component was affected, and for that component we can have that root cause analysis and detailed mapping on the PRA event, whether it had any risk connotation or not. Now in root cause analysis, one is that if an event is happening frequently, I mean it is sort of a having a reliability loss or availability loss, then also it might require, if it is erratic. So there the root cause fraction, or it is happening one here, let us say aging. If suppose in component one component fails here, another component fails in another system, and one more component, let's say pump, and they are failing, so that means there is sort of a aging phenomena has happened. And why that aging phenomena has happened, then so it is a series of question of why and why it was ignored. So we will have higher root cause fraction, that is one thing, and then root cause becomes necessary. Then other is root cause importance. Root cause importance means it has got a risk significance attached to it is very high. Okay, so there are mathematical formulations available. We can see. So one is fraction is increased, and other is risk significance is increased. So that these two, like if I am mapping on PRA model, this event is impacting the core damage frequency. So then it becomes a very important thing. So then what system required? The system required, whatever root cause analysis system in IORM we are suggesting is that each failure is not having the same importance. So 90% of the failures are there where failure has happened, you have got corrective mechanism, and but those 10%, 1% requires so we have to divide them in different categories, and then that will lead to of course through the approved procedures, and of course the root cause methodology itself says interview with the grassroots level people. One is brainstorming session, but then more important than that is, or rather equally important is the grassroots level people who are involved in maintaining those components, operating those components, who were there, were dealing with the modification, and who are working closely with the event altogether. So very important insight we'll get from there. But in spite of that, we have to do RCA can be divided into three parts. Level 1 RCA. Level 1 RCA is that important of the event in terms of fraction or in terms of risk significance is very low, and but it requires attention. Okay, it cannot be ignored. So like in IORM, in 2 weeks time, that means data collection, then we'll have some preliminary analysis, arranging the event in chronological order, and then whether we are able to identify human roots or 2-3 roots we have identified to follow up, and that is sufficient. So it takes 2 weeks time. So 90% of the event will fall in this category. Level 2 root cause analysis is where there is a risk significance or safety significance, but actually it has not happened with this event, but it has potential. Okay, level 2 root cause analysis can be performed. It should take 2 months time, because an element of simulation and testing will be there, and then weighing the new system that is coming in, that also requires attention. And then level 3 root cause. Level 3 root cause is very intensive. There was a risk significance, that means it happened with the safety system, or it had a potential to affect the safety of the plant. Then this type of root cause analysis in IORM experience, it takes 6 months to around that 6 month time it takes, because a lot of modeling, human factor modeling is not sufficient to say that this has happened because of mistake, lapse, or error of commission, error of omission. We have to go down to a level of whether it was a cognitive issue, it was a cultural issue, it was a conscience issue, it was a consciousness issue, attention, awareness, this kind of issues. So we have to go to not only go to, so in IORM, things don't stop at the identified few identified attributes like error of commission, error of omission, lapse, mistakes. No, don't. And see why it has happened. The way we do for hardware components, till we reach the material level, here also till we reach at the level of human behavior, or which component is any issue which can be handled at psychological level or physiological level, and those roots are very important to understand, so that this event should not happen again. So as I mentioned, there are 3 levels in IORM. Level 1 is direct cause. The direct cause could be bearing has failed because of low lubricating oil level, and there could be human error, some lapse, or it was a design problem. The bearing should not have failed. Oil level quality was not good, or level has fallen low, or there was some contamination, or many issues. Or there was a bearing problem also. So this can be understood within 15-20 days time, and it could be training issue if it is a human factor, design issue, control issue, instrumentation issue, quality of oil or quality of bearing, operational failure, some readings were missed in between, and then maintenance issue, it was not installed properly, or organizational error. in organization we should have a checklist for this kind of component, quality assurance program, inadvertent failure or something like random failure, some inadvertent failure, it was by mistake it happened during installation or something, and then intentional failure. So of course this is last one, we will bother about this type of failure. So direct root cause analysis, then typical characteristic of failure, so attitude, timing, cultural, so we've gone deeper into it, and then end of error of commission, error which is a conventional practice, procedural error, violation, mistakes. So normally we come up to this level in traditional root cause analysis, but in IORM we go down to the roots further down, whether it was a issue with the consciousness factor, that is alertness, awareness, including space consideration, negligence, organization culture, risk conscious culture, and attitude and all that. The cognition error, is it that error has happened because it was going beyond the cognitive function? Like if you want to take somebody action in a very time window available is very less, and the time it takes to actually do the job is more, then there is a cognitive factor comes into the logic processing and all that. Was it a knowledge based task? Was the task require knowledge based approach where we have posted only skill based action we expected? So those kind of things are, and conscience, it is related to security, some moral integrity level or some they were in question, so some action was not performed. So these kind of factors, and these kind of factors, I think in my last lecture we had developed a faulty approach to approach at the human roots. So if it is a disease or it is some deficiency or that can be handled. So like we discussed in those lectures, the optics, optics means eyes, we are doing some mistake in some observation, visual observation. Why that happened? Go down to the level of occipital lobe, if it is a brain function or it is a communication error or it is a nervous system. So go to the way we treat hardware component, we should use at least on the same platform the human component also to understand the causes. And as far as level 1 PSA is concerned, it will tell you of the plant. Level 2 PSA will tell you the managing the scenario and the containment for nuclear efforts. And for level 3, it is basically on accident management, where cognitive factors. So there cognitive factor comes predominantly, in support of taking decisions. Now, if we talk about the accident precursor program, so our accident precursor analysis. Accident precursor analysis has come into prominence because there is a need to understand the trend of any structure, component or system before it fails. And I think there is a formal field called prognostics and health management. I'll touch upon that also. So that is required. So in the plant, we can have a precursor anomaly is there. Suppose there is some feeble sound is coming somewhere. So there can be a proactive approach and there could be a reactive approach. Reactive approach will have is something which we do normally. The failure has happened, then incident, and then this path will be followed and corrective action program. But then we lost availability, we lost reliability, or we compromise risk also, because this was initiated after the failure. Then the proactive approach is precursor analysis and human root cause analysis. These two, if it has happened at the human level, the proactive approach is we have provision for those human roots analysis. And for hardware component, it is a prognostics and health management. That means, let us say I have a motor and a motor bearing, and I have installed a temperature indicator and vibration indicator, which are there normally, the plant. So if those signals have given me a meaningful information for temperature rise, I can avoid the failure. I can go to the standby system. Even in a reactive approach also, we have those kind of signal. But as far as the human root cause analysis is concerned, this requires a detail. So postulation of these two require postulation of failures, corrective action program, and finally level 1 PRA will tell us what is the significance of this failure, and accordingly, and the kind of failure, we can have a corrective action program. No or insignificant consequences. So here we have consequences. Of course, here also if we use the signal that are available from the system and it is communicated properly to control room, then we can take all those actions. But otherwise, if I have those monitoring systems available in the control room, I can look at the trend, or on the local panel, I can look at the trend. I will not need alarms and trips to actuate. And before that, looking at the trend itself, I can take the corrective action. Now, these anomalies are in IORM, they are binned. Binned means they are segregated. So what is the criteria for segregation? Because we have to understand the importance of those anomalies. So there are some guidelines in IORM which we have developed. The anomaly that has potential for common cause failure should be given highest priority. Okay, because it disables all our redundancy, kicks off. That means it failed the system it will. So if we have some, but problem with the common cause failure is we do not have much data. So effort should go on to see all the aspects. What was the vendor's requirement for these components that were there, how my environment is there, and if there is a common root available in terms of humidity or in terms of temperature or or a human factor and root cause, they are you can say one should avoid, analyze, and they get the highest importance than the hardware root cause. Primarily mapping of anomaly in PRA model and could be precursor. So here we understand the risk importance of so this can be done easily, and of course in PRA model common cause failure will precipitate it to be one of the top-notch priority event. The anomaly having potential for catastrophic failure after a critical point should be considered. Certain components that do not give any sign of failure or degradation, okay, they fail in catastrophic failure. It is very important to identify the catastrophic failure mechanism and what are the safety margin and beyond which a catastrophic failure will occur. So the prognostics and health management may not work here, because PHM is basically meant for systems where in a gradual manner the risk is increasing. Okay, and then the behavioral attitude, if we talk at the human level or organization level, then general attitude, that point human attitude. I mean, sometimes these symptoms are available in the plant, but we don't have a mechanism how we can adopt it so that they don't harm the plant actually. Screening approach can be based on, and we have to develop the criteria. So plant should have a framework for developing this criteria. Certain event anomaly might lead to analysis for threat potential on conservative basis. These events can be built for proactive approach. And the guidance as above provide the basis for binning these events either for protective or evaluation or reactive evaluation can be ignored for future even can be ignored for future decisions. So what we are saying is that these are the guidelines. Some guidelines can be incorporated, some if they are not applicable they can be but then we have to develop your guideline which should be exhaustive enough to capture categorization of all the events. That's how now as I mentioned, prognostics and health management, how it works by anomaly identified through this one. Now we have anomaly here, but failure has not occurred. So what we do is, what is the failure mechanism, failure mode and mechanism in the analysis, and then online sensor data that is coming. So we are continuously monitoring this system or component or structure, and then online sensors are tracking this thing, and then prognostic algorithms are used, parameters on time, how it is going, and this is the alarm value we have here, but if we can trap it here only or well before that, so after alarm value the time will be very less. And then finally time to failure distribution, what is the time that is available indicated either to touch this or going beyond this, and distribution can be developed and failure prediction can be done. And PHM has become a very ideal approach, especially for electronics component. So not all the components require the same importance, but components which are critical for them, this PHM, like for if you develop for one bearing, so for all plant bearings you can have this prognostics and health management approach. And bearing failure is one of the major cause of any system failure through pumps unavailability to deliver its function. So we had root cause analysis and accident precursor analysis program. We discussed the limitation of the traditional approach on root cause analysis, 3 levels of RCA, insight from PSA, an advanced method like physics of failure, mechanics of failure. This field is developing, and for engineering we can call mechanics of failure, as I mentioned in one of my papers, and here mechanics of failure, and understand why the failure has happened. What were the margins that were given to us, and what should have been the actual margin, and if those margins are available, can we go for next level, that is for 1 year, 2 year, or immediate action are required. Those can be. Similarly, precursor event, they are early warning of failure. So sometimes these two together work together actually. There are 2 approaches for reactive and proactive. PHM approach, proactive approach, has huge potential. It is already being extensively used in remaining life estimation of bearing or other components. Only thing is it requires an intelligent module for prediction purpose.